Section 3-1, solving equations. So a lot of this should look familiar to you, just a good review. If you want for the notes, my suggestion would be to go ahead and try these on your own. So pause the video here in a second, and then I'll walk through the steps of them just as a reminder for you. Okay, so go ahead and pause now and try these two on your own, and then you can fast forward through the video to double check. All right, so this one, when you have variables on both sides, the first thing you want to do is go ahead and get all the variables on one side. It doesn't matter which side you move the variables to. I'm going to move them to the right side here just because that'll give me positive 2p. Okay, so it's 1 plus 2p on the right side, and I have 7 over here. Then I'm going to subtract 1 from both sides, and I get 6. That's a 7 up there, just so you don't get confused. Equals 2p. Then I'm going to divide both sides by 2. And p is equal to 3. So in this section, they just talk about how to solve equations using the same operation on both sides of the equation, stuff that you've seen before in Algebra 1. So with this one, what we want to do here is we want to go ahead and simplify the entire left side of this equation before we do anything else, before we start moving variables side to side. So I'm going to distribute, and remember we talked about in the distributive law section that this negative or subtraction here, if it's helpful for you to write plus -2, you're certainly welcome to do that. So that would give me 1, and when I distribute -2 to 3, that'll give me -6. And now I'm distributing -2 right here to -x. And again, if you want to write plus -x, you can do that to help. That'll give me an answer. Not an answer, but when I distribute, I'm going to go ahead and get plus 2x, and then I still have 10 plus 5x on this side. So I'm going to combine my like terms, 1 minus 6, so negative 5 plus 2x equals 10 plus 5x. Once again, I'm going to move the variables this way, just so I get a positive coefficient on x, just going to make life easier and hopefully cut down on any mistakes I'll make messing around with signs. Then I'm going to subtract 10 from both sides, so negative 15 equals 3x, then divide by 3, so x is equal to negative 5. The other thing it talks about with this first example is that you can obviously take these answers and plug them back in. So if I take 3 and plug it into this equation, anywhere I see a p on the left side of the equation, I'm going to get 7 plus 3 times p, which would be 7 plus 9 is 16. Then on the other side, I'm going to get 1 plus 5 times 3, so 1 plus 15, which is 16, and I know that that makes that a true statement. Okay, picking up here with example 2, there are two parts to example 2, A and B, but they want you to use the same direction. What they talk about in the textbook here is solving for the variable x, which when you have an equation like 2x plus 12 equals 20, pretty straightforward. In example 2b, though, we have multiple variables. So in the textbook, they call this solving equations with constants represented by letters. So instead of having 12 here, we have z, and instead of having 20, we have n at the end. So if you go through the process of solving this, we're going to subtract 12 from both sides. So 2x is equal to 8, then divide by 2, so we get that x is equal to 4. Okay? And then in example 2b, we're going to follow the same process. We're going to move z to this side by subtracting, because to get x by itself, first we have to get 2x by itself. So that gives me 2x equals n minus z, and then the last step to get x by itself is to divide by 2, so you get a final answer of x equals n minus z, all of that divided by 2. So we're isolating x to get it by itself, and we have, instead of just a nice neat whole number answer like 4, we have all of this n minus z, all divided by 2 is what x is equal to in this situation. All right, moving on to example 3. Same situation here. They want you to solve for w, so we want to get that variable all by itself. And one thing that you may notice here, or you should notice, is that W shows up in two places. So it's attached to A by multiplication here and attached to 3 by multiplication here. So the first step is we're going to add 5 to both sides, and I'm still using that highlighter, so I'm going to switch over to the pen. So we've added 5 to both sides. So now I have AW plus 3W is equal to 17. My next step from there is how can I get these two W's to end up as one W? What I'm going to do is I'm going to factor it out. So I'm going to factor out W from both of these and get W times A plus 3. And by factoring out that common factor, now all I have left is one single W on the left side. So to solve from there, I'm going to divide by this entire quantity because I'm multiplying up here. So divide by A plus 3, which means that these will cancel each other out. And that's going to leave me with a final answer of W is equal to 17 over A plus 3. And you'll see some problems like that on the homework where you'll have to use factoring to get a variable by itself. Okay? Example 4 is a very similar problem. 2q squared p plus 5p plus 10 is equal to 0, and they're asking us to solve this for p. So now that you saw how we did the previous one, go ahead and pause the video here and try this one on your own, then come back and check it with my work. All right, now that you've tried this one on your own, we're going to go ahead and subtract 10 first because it doesn't have a p in it at all. So we only want stuff with a variable p on this side. So 2q squared p plus 5p is equal to negative 10. And the next thing we want to do is to go ahead and factor out that p so that we can get it by itself. So when I factor p out from both of these terms, I'm left with p and then parentheses 2q squared plus 5, and that's going to equal negative 10. And similar to the previous problem in example 3, because I'm multiplying by that whole quantity, 2q squared plus 5, I'm going to divide both sides by 2q squared plus 5. So my final answer then is that p is equal to negative 10 over 2q squared plus 5. And we talked about this a little bit as well. This last step here would be legitimate because we can't have 0 in the denominator, but because q is q squared, and that will never end up as a negative, this quantity down here, 2q squared plus 5, can't end up as 0, so we're okay. And as I said, the textbook says that the terminology they use is that this last step or the final answer is legitimate. We can divide both sides by 2q squared because that's never going to be dividing by 0. Plus x. So before we start example 5, there was a comment in the textbook. It says, what other operations can we use to solve equations? This one says to decide whether or not using a certain operation to solve an equation is allowable, we look at whether or not it changes the equality between the two quantities. So we're starting with a statement that says the cube root of x is equal to 8. So that's an equality statement saying that these two expressions are equal to one another. We've solved square roots before, and to get rid of or cancel out a square root, you square both sides. So in this case, you're going to go ahead and cube both sides. Okay? And cube that side there. So cubing a cube root, the effect it has on the problem is that those will just cancel out. So you're left with x is equal to, and then when you do 8 cubed, you're going to get 512. If you do look in the textbook, the first thing they did is they rewrote the cube root of x as x to the 1/3, and we have not got into fractional exponents yet, but these definitely are equal to one another. We'll talk a little bit more about that, but the reason they wrote it as x to the 1/3, sometimes that's a little easier to see than when you cube that. Remember, when you do a power to a power, 1/3 times 3 is 1, so that's where they're getting x to the first, or simply x, and then they cubed both sides. So if you take a look at that one in the textbook, that's why they wrote as x to the 1/3. Actually, I think the textbook used the letter z, so it was z to the 1/3, but same idea. Okay, so looking at another one like this, and we mentioned this, or I mentioned this on the previous slide, you've solved square roots before. I'll go ahead and rewrite the problem right here. So square root of x is equal to -2. And what we want to do from here then is solve by squaring both sides. Now hopefully you're thinking about this as we do it and you say, well, wait a second, if I look at the original problem, the square root of something, if there's no negative sign in front of the square root out here, is not going to end up as a negative quantity. When you do -2 squared and you get 4, you want to plug that back into check. So the square root of 4 is equal to -2. We know that that's not a true statement because the square root of 4 is just 2, and that's not going to equal -2. So this particular problem would have no solution, and hopefully that is a familiar symbol and familiar terminology from Algebra 1. Okay, example 7. Let's slide down here to example 7. And they just give a couple of other situations. Here we have proportions. So when you're going to solve a proportion, there are a couple ways to do it. I'll show you two different ways in this first one, and then there's actually a problem that I added, example 8, where you're going to clear fractions out. So this part of the textbook says equations with fractional expressions. The first way that we've always talked about solving a problem where you have one fraction equal to another is that you can cross multiply the quantities. So you can do 2 times 6 minus x, and that's going to equal 5 times the quantity 3 plus x. Okay, and then from there, one way that the book describes this is we take a problem that had a bunch of fractions, and what we did is we made it into a simpler problem. So by changing what was a proportion into an equation that looks similar to any other equation that we've solved, it's going to be a lot easier to solve. So we're going to distribute the 2 here and get 12 minus 2x, and distribute the 5 and get 15 plus 5x. I'm going to add 2x, and I'm just going to do all this in one step just so I can go through it quickly. That's 7x over here. Then I'm also going to subtract 15 to move the numbers to this side, which gives me -3. So -3 equals 7x, and dividing by 7, I get x equals -3/7. And again, you could plug that in. We'll talk a little bit in class about how you can plug that in pretty easily to check your answer. Now, another way you could do this problem, I'm going to write this another way and then come back and erase it, just so I have room for example 7b. So to start the problem, 2 over 3 plus x equals 5 over 6 minus x. You should also remember from the algebra textbook that you can multiply both sides by the least common denominator. So the least common denominator of these two fractions is 6 minus x times 3 plus x. Okay, so we're going to multiply both sides by that, 6 minus x and 3 plus x. And the purpose of doing that is that that denominator and 6 minus x will cancel, that denominator and 3 plus x, and what you're left with then is 2 times the quantity 6 minus x equals 5 times the quantity 3 plus x, which is exactly what we got when we cross multiplied. So multiplying by the LCD shows you why you're allowed to use cross multiplication. Okay, I'm not going to solve it from here because you've already seen what that ends up as, and like I said, I'm going to erase this just so I can go ahead and use this side for example 7b. So to solve example 7b, I'm going to do something similar. I'm going to go ahead and multiply both sides. So I'm going to rewrite this s equals a over 1 minus x. Since this is s over 1, you could